I'm already exhausted before this is even starting. Okay, so guys, in this video, we are going to be talking about radiocarbon and carbon dating. It's going to be a very long video, so bear with me because radiocarbon dating and everything like that, it's just complicated. So I've done my best to kind of simplify it for everybody, to explain everything for kind of like the newbie in archaeology. So I hope this really helps. That being said, I'm not like a complete expert in radiocarbon dating. So this is just me trying to kind of take it from the textbook form where it can get kind of muddled and confusing and bring it to language that's a little bit more inclusive, let's say. So here we go. Fingers crossed. See you on the other side. Radiocarbon or carbon dating is this really cool, amazing technique that was developed by this chemist named Willard Libby in the 1940s. And people loved him so much for what he did that he actually won the Nobel Prize for it in 1960. So good on you, Willy Libby. What Libby wanted to do was use the known properties of radioactive isotopes, which decay at a constant rate, to measure time, essentially. And God damn it, did he ever. Now you're probably thinking, what the hell is an isotope? I study humanities, for God's sakes. What are we talking about chemistry for here? Here's a quick science lesson for you. The simplest way to put it is that elements have electrons on rings orbiting around a nucleus that is filled with protons and neutrons. The protons and the electrons define the element. They have a specific number, and those you cannot change, because if you changed those, you would change the element. The neutrons, on the other hand, they can vary a little bit. You can have more or less neutrons inside of the nucleus, and that pretty much only affects the atomic weight of that element itself. So these final products with the addition or the subtractions of neutrons are called isotopes. So that means certain elements can have a bunch of isotopes that are, because they're stable with multiple or fewer neutrons inside of them. Some of them don't have as many isotopes because they're not as stable if there are more neutrons inside of them. So it can vary from element to element. But because we're only focusing on carbon dating, I'm pretty sure you can guess which one we're going to focus on. Carbon, as a pure carbon, normally has 6 protons, 6 neutrons, and 6 electrons. It's super stable. Like, it's this beautiful little element that is just so pure, and everything organic on this planet is made up of carbon. Like, I'm made up of carbon, you're made up of carbon, the food you eat is made up of carbon, the trees outside are made up of carbon. You get my drift. So because there are 6 protons and 6 neutrons in carbon in the nucleus, carbon's atomic weight is 12. So that's the original carbon. Carbon 12 is carbon. But carbon has 2 other isotopes that it can form. There's carbon 13, which is an extra neutron inside of it, and then there is carbon 14. The first 2, carbon 12 and carbon 13, they're very, very stable. But carbon 14, it doesn't really like that you put 2 extra neutrons in there, so it's getting a little angsty. It's unstable, meaning that it is radioactive. And all 3 of these isotopes occur naturally within the world, but in varying quantities. So about 99% of all of the carbon in the Earth, on the planet, is carbon 12. About 1% is carbon 13, and then a very, very tiny trace of other carbon is carbon 14. Like, it's so tiny that we need to use an exponent to describe how tiny it is. Okay, and that exponent is 1 to 1.5 atoms for every 10 to the 12 carbons in the world. So you take a 1 and then you add 12 zeros after it, and that's how few carbon 14 atoms that we have in this world. Like, it's ridiculous. Super tiny amount of carbon 14. For every 10 to the 12 carbon 12 and 13 atoms that we have about 1 or 2 carbon 14 atoms. Now you might look at this number and think that it's impossible or silly to use such a small, minuscule amount of atoms to measure time and dating things. But if you think about it, a person who weighs, let's say, 70 kilos, they have 7 billion, not just billion, billion carbon atoms inside of them. So you can see where we would probably be able to get enough carbon-14 inside the body or in anything else organic, really. Carbon-14 atoms are unstable because they're essentially having an identity crisis. They're actually created from nitrogen atoms that were chilling in the upper part of the Earth's atmosphere. Nitrogen makes up 78% of the Earth's atmosphere, so you know they're just having a heyday ruling the world from up there. But what happens is that subatomic particles come from the sun, and they come, bumping around, and then they eventually form neutrons with all the other elements that they're bumping around in. Then, once in a while, one of those neutrons will come in contact with a nitrogen atom, and they'll bump into it at just that right angle that will end up bumping out one of the protons from the nucleus of the nitrogen atom, okay? If you're having trouble visualizing this process, think about those health class videos that you used to watch in high school where you see all the sperm kind of enter the uterus and kind of bump around and race up to the egg. That's essentially what's happening, okay? They're all kind of bumping around. Eventually one, hopefully sometimes, makes it in. Now, it is a challenge, yes, but it can happen, and once it does, it can create something entirely different. And of course, you can't have a nitrogen with 6 protons. It doesn't exist, so now you have carbon-14. And this is constantly happening all in the atmosphere. It's just something that happens naturally all the time. The sun is just powerful. So now this atom is all confused. It just had this whole identity change, and it's deciding to act like an angsty teenager. And rightly so, I might add. Its proton-neutron balance is all off, which means that it can get quite unstable. These carbon-14 atoms are then floating around the atmosphere, probably listening to My Chemical Romance, Linkin Park, being upset at everything, and eventually they will bond with an oxygen. And this will create molecules that we are very familiar with, carbon monoxide, carbon dioxide, etc. And then every so often, one of these molecules will get absorbed by a plant through photosynthesis, which is why we need to keep the trees alive, guys. Then, of course, the animals eat the plants, and they eat a lot of plants, so then they gather more carbon than a plant would. And then an animal who eats animals would then eat that animal, which has all the carbon, and they would absorb their carbon, and they eat a bunch of animals, so they get even more carbon. It goes on and on and on, and eventually it makes its way into your bloodstream throughout your whole body. It goes into your bones, your teeth, everything. And then once the carbon-14 has found a nice home, it then settles in a little bit and it decays back to its nitrogen, okay? So the neutron is then turned back into a proton. This part is a process called beta decay. It's very sciencey, and I've left a useful link and a video on the write-up in my website for it. This thus concludes the puberty phase, and the newly returned nitrogen goes on to live a much more stable life with hopefully some better choices on music and makeup. All of this is constantly happening over the life of a living organism. We are constantly absorbing, decaying, and expelling carbon-14. And just by living, we are constantly renewing our levels of carbon-14. Because every time we eat, we ingest new carbon, it decays, we eat again, new carbon, etc., etc. This goes on until we die, and that's when the archaeological stuff comes into play. When we die, there's no new carbon coming in, no new carbon getting absorbed into our bones, anything like that. So the carbon that's already inside the bones continues to decay. And this carbon-14, this radioactive isotope, decays at a constant rate. And this is what Willard Libby found out back in the 1940s. We can think about this concept as either a timeline or a clock, whichever you prefer. If you think of food at a grocery store, it has something called a shelf life, a time period that it will remain, fresh and juicy. And after the shelf life, it begins to decay. And of course, different foods have different shelf lives. Carbon-14 doesn't really have a shelf life per se, where we have an exact date where we know it goes off, but it does have something called a half-life, and a very specific one at that. 5,730 years. So that means at the end of every 5,730 years, the radiocarbon atoms inside a dead organism will be half of what were there at the beginning of those 5,730 years. So if we have 100 carbon-14 atoms at the time of death, after 5,730 years, we would have 50 carbon atoms. But of course, after 11,460 years, we would have 25 atoms, and so on and so on. It goes on until you get like these tiny, minuscule amounts that are even too small for us to measure. As an archaeologist, when you dig up anything organic, like a bone or a plant matter, piece of charcoal, things like that, it needs to be dated in a lab. And what they'll do is they'll take a sample and they'll use an accelerator mass spectrometer, or AMS for short. What the machine does is that it accelerates the carbon isotopes and it counts the carbon-12 and the carbon-14 atoms. And the fun thing is that carbon-12 doesn't decay. So it's a perfect benchmark to measure the carbon-14 in a living thing. What you can then do is compare this ratio to the carbon-14 atoms that you would expect to find in a living thing of similar type that you are studying. And based on that, you get an age of that object. Now, I'm sure you're already screaming at your screens, aghast at all these assumptions that I've been making. Here's the thing with radiocarbon dating. It heavily relies on two major assumptions. One is that carbon-14 decay occurs at a constant rate. And two, that the ratio of carbon-12 and carbon-14 atoms in the atmosphere has remained constant over time. Now, the first assumption, that one is pretty accurate, like really accurate, okay? Science has already tested this one over and over again, so we don't have to worry about that one. But the second one, the carbon-14 ratio remaining the same, this one can get a little bit tricky. The truth is, no, it's not perfectly constant, because remember, the reactions with the nitrogen atoms in the atmosphere, yes, they're happening all the time, but they're not happening at a constant measurable rate. For example, if you look at tree rings, you'll notice that the atmosphere had a lot more carbon-14 in it before 1000 BCE than it does today. And this is why it's always very important to calibrate your carbon-14 dates with other dating techniques to make sure that it's more accurate. Raw radiocarbon dates, the dates that you get right from the lab, are reported in years BP, before present. Present itself is set at 1950 CE because the present is always the present, and that can get very confusing when you're trying to, calibrate a date. So they set it at 1950. They chose this date because that was around the time that Willard Libby was doing all of his experiments and working out how this method works. But it's also because after this date, we had a lot more nuclear testing, and that just messed up all the carbon-12 and carbon-14 in the atmosphere. Really messed it up. But that doesn't mean carbon ratios weren't perfect before nuclear testing either. Levels have fluctuated forever. Sunspots, for example, can be a cause for this. But also, we've been burning crazy amounts of fossil fuels for the last 300 years. So even 300 years ago, we were already messing up the carbon levels in the atmosphere. So that means, of course, radiocarbon dating on its own is not the most reliable. But we're able to use other dating techniques, depending on what material we're dating, to calibrate this radiocarbon date and make sure it's more accurate. One of the more popular techniques for landscape ages, for example, is dendrochronology. Within the tree rings, we're able to measure the carbon-12 and the carbon-14 for each year, going back thousands and thousands of years. So it really does help with calibrating those dates. With this information, radiocarbon dating gets a heck of a lot easier. The second way is to use speleothems, which are cave deposits made up of calcium carbonate, which means they have measurable carbon inside of them. This is very exciting. We can use them up to 50,000 years ago. With radiocarbon dating itself, after 50, 60,000 years, it doesn't really get very measurable anyways, so it's perfect. With all this data, we can then use databases for people to plug in their BP dates and then get a proper date range for their tested object. And of course, I need to stress that it is a date range and not an exact date because of all of these limitations that we just talked about. Usually, labs will already give you a calibrated date, and it'll look something like this. So the BP, of course, is the before present, before 1950. We know about that. And the plus minus thing is the range. So between 100 years before and 100 years after 2400 BP. Anyways, we put this date range on a graph alongside the carbon measurements that we've gotten from that dendrochronology or the speleothems. So one axis has the BP dates and the other axis has the regular calendar dates, the ones that we use every day. Next, we draw two horizontal lines where the plus and the minus dates were until they meet the carbon. And then right where they meet, we draw two vertical lines down. And the space between these two vertical lines is now the date range for the calibrated calendar years. And this is a pretty wide date range, but with the wide date range, we can say it's about 95% accurate. So that's pretty good. If we want to narrow it down a bit and get more of a precise date range, of course the probability lessens, and that goes to about 68%. So yeah, it's a complicated process and it isn't completely accurate, but it is one of the most important things that we have to date organic materials. Think of, human and animal remains, but also things made out of organic objects like tortoiseshell combs or purse handles, leather goods, even though that leather can be a very rare find, charcoal from a fire. All of these things can be dated using radiocarbon dating. We can even use organic finds to date inorganic materials, all thanks to an archaeologist's favorite thing: context. If a carved stone or some piece of pottery are found together with an organic object, the dates of both of those objects are probably going to be the same if we correlate the carbon-14 with the other forms of dating techniques, especially the ones that we can use for inorganic objects. What a tangled web we weave, eh? There's just one other thing we need to look out for when doing radiocarbon dating, and that is called the old wood effect. Wood is a great example of an organic material that can be used or repurposed over a long period of time. If you're using wood to build a house, you're usually using the inner wood from the log, which, if you've seen my dendrochronology video, you'll know is the older part of the wood instead of the outer side, which is much newer. So that means the inner bit is older than the time that you are now building the house in. The house could then stand for hundreds of years. It could be a long time before it burns down, collapses, or gets repurposed before it falls into the archaeological record. The same goes for family heirlooms and antiques. Objects could be passed down for generations before entering the record. And this is why we can't look at objects individually. We need to look at assemblages and all of the objects in relation to one another in order to get a proper idea and interpretation of the finds. Carbon dating has provided the most useful way of answering the when question in archaeology. And while it has its flaws, this method can be used all over the world as it only relies on uncontaminated organic materials. And it can also date back to 50,000 years ago, which is very, very important. This method has been used for cultures that don't have written historical records or timelines to put things into context. It's been used on cave paintings, on torch marks, and even on some more controversial objects like the Shroud of Turin. It's crazy to think that you can get so much information out of a sample the size of a grain of wheat. But there you have it. Science is pretty great, huh? So that's been carbon dating. Thank you for holding out with me through this video. I know it was probably a mouthful. It was a whirlwind to explain, but hopefully you were able to stay on track with me there. If you're learning about this in class, don't give up. It can get complicated and confusing, but there is a whole write-up on my website. I've also added a bunch of extra links, a bunch of videos to help you kind of grasp it and explain it. So do not fear the radiocarbon dating. Don't forget to subscribe to my channel. And if you like these videos and what I do, consider becoming a patron on Patreon so I can up my game and continue to bring you amazing content. You also get access to a lot of cool behind the scenes content too. These are all my socials, and as always, stay dirty, my friends.